In May 2025, we got a first-hand look at what a missile defense system looks like during a major international conflict, when Israel attacked Iran out of the blue and prompted a retaliation. This system is often called the Iron Dome, but the Iron Dome is actually the lowest and cheapest level of this missile defense system, consisting of 10 batteries costing around $100 million each, with each missile it fires costing around $40,000. Which is actually incredibly cheap in comparison to the $4 million interceptors used in the United States Patriot missile defense batteries. And recently, the United States began planning to imitate the marketing of this system, branding their own system, the Golden Dome. But there is a problem. This is a Qassam rocket, the most common rocket fired out of Gaza. It's a small rocket that runs on sugar and potassium nitrate fertilizer. And this is a hypersonic glide vehicle. One cost $800 and was developed by impoverished people within the confines of the walls of Gaza, meant to travel unguided a mere 16 kilometers. The other can fly from anywhere in the world, reach the limits of space, guide itself back down and maneuver inside Earth's atmosphere, dodging attacks and guiding itself with an incredible degree of accuracy to its target halfway across the Earth. The high cost of the Iron Dome system would pale in comparison to a system meant to defend against these larger, more sophisticated threats. The need for this defense system is hard to justify, considering the US has never had to defend itself from missile attacks on its own soil. So, what is the Golden Dome system? How will it work? And how much can it truly protect a country as big as the United States? The Golden Dome is expected to counter a wide range of advanced threats, including ballistic missiles, hypersonic glide vehicles, and cruise missiles. The project is expected to cost anywhere between $161 billion and $542 billion over a 20-year period, equivalent to 6 to 27 years of NASA's entire operating budget. So how do systems like this work? The Iron Dome was designed to intercept rockets and artillery. At the heart of the system is a self-contained radar, capable of detecting and tracking a wide range of threats. When a threat is detected, the radar sends the data to a battle management and control unit, which quickly calculates the projectile's trajectory. If the system determines that it's headed towards a populated area or a critical infrastructure, it responds with a Tamir interceptor, which guides itself to the target using the ground radar data and its own optical sensor. It's common to call the entire missile defense system the Iron Dome, but it's just the last part of a multi-layered system. The Iron Dome only covers the lowest altitude layer, with David Sling handling medium-range threats and the Arrow system managing high-altitude, long-range ballistic missiles. It's this Arrow system that is currently under incredible strain as Iran retaliates to Israel's attacks, with some missiles getting through as the system is being overwhelmed. And with interceptor missiles running low, this could get worse, with reports that it's costing Israel $285 million a day to keep the system operational, with the Arrow system interceptors costing $3 million each. One of Iran's newer missiles is called the Fatah. They label it a hypersonic ballistic missile, but that's a bit of an overstatement. The hypersonic description of missiles usually refers to the highly maneuverable rockets that fly low in the atmosphere and are able to shift direction mid-flight. The Fatah, by contrast, follows a high arc, like a ballistic missile. It does reach hypersonic speeds on re-entry, but so do most ballistic missiles. The Fatah can maneuver slightly, but it's not on the same level as a hypersonic glide vehicle. The real challenge comes from numbers. Iran's strategy is to overwhelm the missile defense system by launching 100 to 400 missiles at once, along with waves of cheaper drones that clutter radar systems. The Iron Dome also has the advantage that it's defending a small country where cities are close together. The missiles and attacks that could be launched against the US are much more complex than anything launched against Israel. In the event of a war, the US will need to defend against long-range ballistic missiles, intercontinental threats, and increasingly hypersonic weapons. The executive order lays out an ambitious plan. It goes beyond building a single defensive wall, aiming instead to create multiple layers of protection for the continental United States. Each layer is designed to handle different types of threats, working together to stop attacks from every angle. Parts of the plan focus on upgrading existing missile defense systems and integrating them into a unified strategy. Other sections propose bold and controversial new ideas that could reshape how the US approaches missile defense for decades to come. A missile's flight is split into 3 key phases. It starts with the boost phase. This phase is short, just a few minutes before the missile reaches space. Then comes the mid-course phase, where the missile travels through space. This is the longest and trickiest part. Some missiles drop decoys or multiple warheads, and some can even change direction, and defense systems have to figure out what's real and what's not. The final stretch is the terminal phase. The warheads plunge back into the atmosphere, racing towards their targets. There's only a few seconds to react. One mistake and it's too late. Before any interceptor can be launched, the system has to know a missile is coming. That starts with detection. One of the clear signs is the heat from the missile's engines during the boost phase. This intense heat can be seen by infrared sensors in space. The job of watching for these launches falls to the space-based infrared system, operated by the US Space Force. It uses a network of satellites in geosynchronous orbit and highly elliptical orbits. These orbits give the satellites persistent coverage over key regions of the planet, especially high-latitude areas that are harder to monitor. Once a missile is detected, the next critical step is to track its path in real time. By watching how it moves, defense systems can quickly figure out where it's going, decide if it's a threat, and send interceptors to the right place to stop it. This tracking relies on a mix of sensors, some in space, others on the ground. Each plays a role, using different technologies to follow the missile's speed, altitude, and direction. As the missile progresses through its mid-course and terminal phases, ground-based radar systems join in on tracking. There are radar stations scattered all over the world, but one stands out most. This is the Long-Range Discrimination Radar. This futuristic-looking phased array radar is located in Clear Space Force Station, Alaska, strategically located for maximum field of view in the direction of expected attacks. Phased array radar, like those used in the F-35, have hundreds of tiny antennas. We can see metal plates set in rows in the F-35 phased array antenna. The metal plates have slots cut into them, and each and every one of these slots is an antenna, 1,600 in total. This allows the phased array antenna to steer its radar using constructive and destructive interference. It also allows the radar to track multiple objects by splitting the radar into smaller subsections, or combining them into one huge radar when needed. This radar in Alaska is made from gallium nitride because it can handle a huge amount of power running through it, while conducting the heat it produces away quickly. This material has even made its way into electronic chargers, allowing them to be much smaller, doing away with the massive power bricks of old while enabling incredibly fast charging. But in this case, it makes for a more efficient radar with longer range and higher resolution. This is incredibly important because in the mid-course phase of a missile's trajectory, they often deploy decoys, which can be as low-tech as nuts and bolts to distract and confuse radar. This radar in Alaska is designed to operate at both lower and higher frequency, allowing it to track at longer ranges at low frequencies and switch to higher frequencies to increase the radar resolution, allowing it to better discern between decoys from actual threats. This is just one of many radars integrated into the Space Force's missile defense system, with others like the massive floating radar operating out of Honolulu on a self-propelled platform. Once a missile has been detected and tracked, the final and most critical step is interception. These interceptors don't use explosives, but kinetic energy to destroy the warheads, and for good reason. First, an explosion could potentially detonate the warhead, which could be nuclear, chemical, or even biological. The goal is to rip the warhead to shreds and disable it. Next, these interceptions can occur at very high altitude, where there is little to no air, where explosives would be less effective. Not because of the lack of oxygen. Explosives have all of the oxidizer they need in their chemical structure. That's what makes them explosive. But because explosions need air to propagate the blast wave. The explosion would only be effective if it was within range of the shrapnel or the thermal blast. which is incredibly hard to time when your target is veering and steering at hypersonic speeds. So, a massive hailstorm of hypersonic debris is the chosen method of destruction. For this to happen, the Interceptor needs a way to track and detect its target too. Older systems used a spinning disc with alternating dark and light stripes. This disc spun in front of an infrared detector. As the target's infrared signature passes through the rotation pattern, it creates a fluctuating signal. If the target was off-center, the signal pulsed in and out of phase with the spin. The signal would only remain steady when the target was centered. Modern systems use an array of sensitive photodiodes that work more like a camera. These detectors are made from indium antimonide, a material sensitive to infrared. They produce a black and white thermal image, allowing the missile to lock onto the target. All of these steps can be neatly packed into a single system too, like the Aegis system that is deployed on US Navy destroyers and cruisers. Aegis's land-based equivalent is THAAD, and all of these systems share information and create a digital 3D battlefield map over the entire planet, incorporating data from every sensor possible, whether it be from satellites, planes, or radar. And this data can even be fed into an F-35's augmented reality helmet, so the pilots of F-35s can see things no other pilots can see. So, the US already has a pretty robust missile defense system. But the executive order for the Golden Dome seeks to increase the coverage of this system significantly, and the order contains one specific line that brings more questions than answers. It states that the Golden Dome should protect against counter-valued threats. A counter-valued threat refers to an attack aimed at targets with high civilian, economic, or cultural importance, such as cities, industrial centers, or infrastructure. The goal is not to disable military forces directly, but to cause maximum psychological, economic, or human damage. This marks a shift in priorities, from protecting military assets to defending civilians directly. Instead of covering the entire country, the plan adds an extra layer of protection around major cities. This means it's now the government's job to start adding priorities. Which cities will be covered? What criteria determines whether extra protection is needed? Is it population size? If so, what's the threshold? 1 million, maybe less? You might not hear about it, but one day, a missile defense system could quietly appear in a city near you. This approach is similar to the Iron Dome, designed to protect specific areas during the final moments of an incoming attack. THAAD handles high-altitude threats from long range, but it's not effective at stopping low-flying missiles, drones, or cruise missiles. That's where the Patriot system comes in, covering the lower altitude layer and providing a final shield for high-risk targets. Like THAAD and Aegis, the Patriot uses a phased array radar. What sets it apart is its ability to use different types of interceptors. The PAC-3 relies on direct impact to destroy incoming missiles, while the PAC-2 detonates near the target, creating a cloud of high-speed fragments to take it down. In Ukraine, Patriot systems have played a key role in intercepting both ballistic and cruise missiles, adding a critical layer to the country's air defense. But these systems are expensive to operate and their coverage is limited. Each PAC-3 missile costs nearly $4 million, so while the system is highly effective, every launch has to be carefully considered. These systems are all technically mobile, but they can't move quickly. This is where the F-35 comes in to fill the gap. More than just a fighter jet, it acts as a highly mobile node in that digital battlefield map, and it can perform every step of the process too. With its radar, the F-35 can detect missile launches in ways that stationary systems cannot. It can pick up heat signatures of a missile engine, the faint radar trail of a low-flying cruise missile, or even the shockwave of a hypersonic vehicle traveling at high speed. Because it can fly close or even inside contested airspace, it can detect and track these threats earlier than ground-based systems ever could. But the F-35 does not just stop at seeing the threat, it shares what it knows. In the Golden Dome framework, this aircraft becomes a flying command post, using encrypted data links to transmit life-tracking data to other systems. And, if needed, the F-35 can do more than just pass the message along. It can take the shot. Equipped with air-to-air missiles, it has the ability to engage and destroy missiles mid-flight. Future upgrades may go even further, integrating high-energy lasers that could target threats without relying on traditional interceptors. That means fast, flexible response options against drones, cruise missiles, or even high-speed threats. All of these technologies already existed, but where things get truly controversial is where the Golden Dome executive order demands new technologies to be deployed. These systems all have one major weakness. They all target the threat after the boost phase. And because of that, one line in the executive order stands out most. The order demands Congress to fund the development and deployment of capabilities to defeat missile attacks prior to launch and in the boost phase. That means Golden Dome will need global interceptor coverage, and that requires the US to cross a line that many do not want crossed: weapons in space. The only way to guarantee a successful boost phase interception anywhere in the world is to deploy a constellation of interceptors in low Earth orbit, ready to respond instantly to any launch. It's the only approach with the speed and coverage needed to stop a missile at its most vulnerable moment. This has been proposed before. Reagan wanted to do it during the Cold War and introduced projects that were never launched, like Rods from God and Brilliant Pebbles. But things have changed since the 80s. Mainly the launch cost per kilogram has decreased drastically. However, this is still the most uncertain part of the proposed system. We don't know exactly what kind of interceptors would be deployed in space, how they would operate, or how effectively they could engage a missile in the boost phase. Or perhaps most importantly, how the world would react to weapons being placed in space. To provide global coverage, the satellite constellation would need to be large. Estimates range from 1,300 to 2,000 satellites in low Earth orbit. While this was deemed too expensive in the 1980s, this is now not just feasible, it's already been done. Starlink already has 7,000 satellites in orbit. However, an interceptor satellite would be more complex and expensive than any communication satellite. The working mechanism of the interceptors is still up for debate, but we can look to the past to guess what the future might look like. Brilliant Pebbles was proposed in the 1980s, consisting of a central kinetic strike vehicle surrounded by fuel and oxidizer tanks that would power the weapon to its target before falling away. In orbit, the interceptor would have remained inside a protective shell called a life jacket, which included solar panels, a star tracker, and a laser communication system. The project was cancelled during Bill Clinton's presidency due to inadequate funding. Putting what are essentially air-to-air missiles in space would not go down well in the international community, especially as there is no guarantee the US wouldn't use them for offensive purposes. But perhaps there is a less egregious way to achieve this goal: lasers. Lasers destroy targets by focusing high-energy beams of light onto a small area, rapidly heating the surface until it weakens, melts, or explodes. This process can disable critical components like guidance systems or fuel tanks, causing the missile to break apart or veer off course. With the energy traveling at the speed of light, it allows for near instant engagement once the laser is aimed and locked on. Incredibly useful for fast-moving, hypersonic targets. The US has already tested an airborne, high-powered laser attached to a Boeing 747. The system successfully demonstrated its ability to shoot down ballistic missiles in the boost phase by heating and rupturing the structure mid-flight. So, instead of shooting down missiles with other missiles, these satellites could include lasers to burn up missiles instead. However, the system would need a lot of power. The US Navy's Helios laser, installed on the USS Preble, is a 60 kilowatt laser, but that's the output power, not the power draw. It's expected that a spacebound laser would need anywhere between 250 kilowatts to 1 megawatt. 250 kilowatts is around the maximum power generation of the International Space Station's massive solar arrays, but their average power barely satisfies half that power need, and we would need thousands of these in low Earth orbit. However, with launch costs lowering, there are several companies right now that want to place massive solar arrays in geosynchronous orbit and then transfer that power from these centralized solar arrays to where it's needed, using microwaves with much higher power densities. So, in theory, a secondary power layer constellation at a higher orbit could allow these satellites to be smaller, operating at lower standby power settings until the laser is needed, at which time power could be directed to them. But needless to say, this isn't going to be a popular solution either. Experts question whether such a complex global missile defense system can realistically be built on the proposed timeline. The initial budget estimate of 175 billion is already being challenged. Other, more realistic budgets project the cost could exceed 542 billion over the next 20 years, raising concerns about long-term feasibility and funding, at a time when major political battles are being waged over US debt, including between the primary launch provider CEO and the president. The project's first 25 billion is tied to a broader 150 billion defense package, which is still making its way through Congress. Without that funding, the Golden Dome could face early delays or scaling back, just as it did in the 1990s. There are also geopolitical risks. China has strongly objected, warning that the Golden Dome has offensive implications and could trigger an arms race in space. Russia has echoed those concerns. And not to mention, these countries have anti-satellite weapons and are likely willing to use them if needed, which could cut off space for the entire planet if a battle was waged in orbit. Which again, I think we can all agree, isn't worth the cost to start wars none of us want. If you are watching this video, there is a pretty high chance you're an engineer, or you just like free things that are usually incredibly expensive. But today's video sponsor, Onshape, is giving 6 months of their professional design software away for free with my link, onshape.pro/real-engineering. Onshape is fantastic for both robotics projects and professional level designs. Design software is typically really expensive and can often require a powerful computer to complete the more processor-heavy tasks like finite element analysis and rendering. I've been using one of my oldest laptops that I've set up in my garage for my 3D printer, and it runs without an issue because it's all done through the cloud, not locally. And it solves other problems too, like keeping files up to date for large engineering and sales teams. Because it's fully cloud-based, everyone on your team can access the latest version of a design anytime, anywhere, on any device. And that would have saved me a ton of headaches when I was sending CAD files back and forth with sales teams and suppliers in my old job. On more than one occasion, sales teams sent out outdated files. And now Onshape has launched Onshape Government, a version of their platform that is ITAR and EAR compliant, making it a viable option for defense contractors and any teams working on regulated or export-controlled projects, like a highly secretive military space constellation, for example. Whether you're designing complex systems at work or building your next robotics project at home, you can try Onshape for free at onshape.pro/real-engineering, or just click the link in the description.